Alright, what you see in front of you is a selection of mud fossils. And mud fossils are literally petrified parts of bodies of creatures. And there is no dispute about this. This is it's been DNA tested. That is a human lung that's been DNA tested. And you can see the pleura. That is the way the lung invests itself. And there's the depression of the heart and everything. This is the fabric, and it's been DNA tested, 100% human. It has that investment at the top, the investment at the bottom. There's no dispute about that. This has also been DNA tested and CAT scan, and the vein and artery are there. That is the bone silhouette of a phalanges, and it steps out and goes out like that. It's just what it is. Now, the arterial side blows out in the fingers because they're very, very dense with blood. You can see how much blood runs in somebody's hands, and they blow out the arterial side, but not the venous side, because the veins, as you can see them here, have pinchers to pinch them off. This is that triangular investment that is where the ligaments invest so you can articulate your fingers. Now, and that's a giant phalanges. This has also been DNA, not DNA tested, but CAT scan. And the nail bed is here, and the apical tuft, and the pads of the left thumb. This is a left thumb, exactly like this. And the nail bed is right here. It's all been CAT scanned on a place that does, it's Jesse Garant and Associates, some very, very, very nice people. And they do engines, racing engines, and all kinds of industrial things with these extremely sophisticated scanners, 3D, color, the whole 9 yards. And they did a bunch of these for us, and they did them in interest of science. And fabulous job, and I have the CAT scans. And they were looked at by a person that goes worldwide and teaches autopsies to all around the world. Last I knew, he was in England, Scotland, somewhere around there. And he looked at this, he looked at everything here, and he agrees with everything I'm saying. Now, this is a lung that's been, all of the volatile organics inside have been washed away, probably by some kind of volcanic activity. pH is what does this situation. Some of them come filled with the stuff and it petrifies, such as this. That's another lung. All right, these are lungs, and I got a ton of lungs. Here's another one right here that is partially deteriorated. You see the pleura is coming off. Now that will turn blood red because it's saturated with blood, and this is too. And all of this stuff is saturated with blood. This will turn blood red. It rehydrates. Here, I'll shoot a little water on here, and you'll see in a couple seconds it'll turn red again. You see, look at it. Now, that's just the way blood works. It transfers oxygen around your body, and it goes from the Fe2 state, Fe3 state, which is oxygenated inside your lungs and through the pulmonary, cardiopulmonary system. It pumps it around. See, look at it. Now, I had some here. This one here turned so red, it bled out of here. Now, that was years ago, so I don't think it's going to do much anymore. But my point is that there's no such thing as you can't get blood out of a rock. Almost every rock contains blood. And the things I am showing you are not disputable. The chemistry is there. The DNA tests have been done. The CAT scan's been done. I've recreated the process in the lab that recreates a feldspar, and that's the result of the silicon, which is dense in your skin, 50 times more in your skin, silicon, than in your tissues. And when the silicon gets in the water, in the, what they call solvomorphism, in the it bonds. You see how shiny these little silicon crystals are, and strappy looking? They bond with oxygen, so you get SiO2, which is feldspar. It's just a natural thing. And the reason they bond so easily is because there's these spontaneous potentials in the earth that drive the bonding of silicon to oxygen. Once this, like this is a finger, once this finger got plated, the contents got stored. Everything's in here if you look at it really carefully. And what happens is blood turns into garnets, and blood has shot out of the end of this finger. Same thing it does to a lot of things when they die. Hold on a second, let me get a better It's totally a natural process, and it's fully understood. It's nothing I'm making up here. And there's a vein and an artery in here. One of them's red and one of them's like clear. You got to look at stuff. But what happens is these things get invaded by the wet conditions, and the bones turn into other materials because they get, there's all kind of different invasion techniques, nucleophilic and ionic and crystalline polar, all that business. And sometimes they're in geological thermal areas like geodes. And what happens is that's a bonehead, and that's what almost all these geodes are. They're boneheads. And that is the actually cap after the stuff boils away, and literally the soft tissue boils away. You end up with a vein and an artery. Here's your artery right there. I mean, I don't know how they could have missed this, to be perfectly honest with you. That's your artery. And that boils out because that's the way it works. And there's your vein, which always shoots out the black blood. This is what it is. And then the inside has boiled away, all of the stuff has boiled out of there, the volatile organics, and there'll be some seeds of metals inside there, and those metals will grow into crystals, and that's why they find all these different crystals inside of geodes. And the reason they find them is, here, let me put a light on this. And the reason they grow is just like when you grow, what do you call it? See, look at that thing. It didn't just, that's so much of an artery, it's amazing. And you can see a little bit of the red that's worked its way out of that. But this is the black, and the black is always from the depleted blood. And this is what this is, a bonehead. And there's the cap type, calcified cap. And then inside of there would have been the spongy bone, they call it. And that boiled out, and then you end up with this. All right, by the time I'm done, you're going to be able to go out in your backyard or in the woods or wherever there's some rocks available and find some rocks and identify them as body parts of creatures. And I can absolutely guarantee you within 15 minutes you will have something in your hand that was a fossil of a living creature, and you will probably be able to easily identify it. Now, do not look where there's dry, porous stuff. That's where bones are, and everything gets, you get all kind of little bugs down there. They eat every little thing. That's where they look, and all they're getting is scraps of bones. Where you want to look is in the wet, fine muds. And the wetter and the finer, the better. The clays are the absolute best because they're very, very thin, tiny little platy polar silicates, and they are what yields mud fossils. Now, whatever is in the water of that particular medium, which is clay or very fine muds, will also invade the tissues of the body, because the tissues of the body, that's how they work. They can continuously pass and taking this in, giving that up, take some oxygen, give some oxygen up. Now, what you're going to be looking for is blood, because blood has to service everything that's in a living creature. We know this. So this is what we're going to look for. And blood is very, very simple to find. Your vein blood is always black in these mud fossils, and your here. Let's see if I can get a little light on this. What you're going to see here is a vein and an artery at the bottom. You see the one on the left? It's been scratched up a little bit. It has black. Watch. You turn that wet, and it turns black. It's black, and that's the black as the ace of spades. That's your, and the other one on the other side is from the artery, and the artery purges out because it doesn't have clamps inside of it. So that's what happens, and I have a lot of examples of this. It's not just that, and some of them still have the veins literally inside of them, which this one does. And at any rate, and they've been DNA tested and all that stuff. So what we have here is blood, where there's a lot of blood, that turns into opals and some spectacularly colored crystals. Now, cold and wet is one type of a preservation condition. Hot thermal and wet is another type of preservation condition. pH is very sensitive to what is flushed out of these and what stays in. That's exactly how your body works. Your blood works in a range of around 5.6 pH up to into the alkaline area. Well, anyway, it changes back and forth. So it gives up some, it takes some on. When it does, it goes pretty much from alkaline to acidic and back and forth. Now, so and volcanoes and that type of acidic stuff will leach these things right out, similar to what happened here with this. There's still some blood in there. You can see that very, very red. That's where the iron oxides are from the blood. This was a lung, and what happens is they leach out all of the organic stuff, and it leaves the skeletal remains, which is the calcium and connective tissue, sort of membrane-ish stuff. Now, other preservation techniques will preserve the whole thing in its entirety, just like it came out of the ground. And I have one around here somewhere. Well, here's this one. I mean, if you look at it, you really couldn't tell that it. I mean, it's been out of the ground for a while now, and it's turned sort of brownish. But all of the structure of the meat is in here. The fibrils, there's little black elastins in there. I don't know if you can see them, but there's black little strappy elastins, and all of the architecture and all of the fascia. This is the fascia flap right there that invests and holds, so your organs and your meat and stuff, it pulls on it. It's really a whole new system they're looking at now, and all the tendinous material. And here's blood literally moving through a piece of meat. This was a piece of meat, and the red blood, it starts over here. Now, of course, it's rusty and it's turned not red anymore because it oxidizes. But it starts to lose its blood, its oxygen, as it moves across to the vein side, and the vein side right there picks it up. And by the time it hits there, it's black as black can be, and you can see that. And you can see it's littered with vesicles or vessels, blood vessels. And over this side is where the red blood enters. And this is the skin on the outside, which contains all those little black dots, are silicon. And the silicon is embedded in the fabric of the skin, and it's just the areas that are very dense and areas that are very light. And all of these things are easily seen, and they're in literally all rocks. The rocks you find are from life. And here's another one. Here's a bonehead that is a fully articulated bonehead. It still has the what do you call it, the cartilage, and of course either that's the blood supplies or the nerves. Then it has ligament areas where the ligaments attached, and bone foramen on the side where blood entered and so forth. And on the bottom you can see there's just the tiniest bit of bone left right there. Whoops. Right where my thumb is, right there. And in the microscope you can see it. It's probably hard for you to see here, but what happens in the mud fossils is it's completely replaced with minerals. They invade the surface, and they invade in a specific way. It's very, very easy to understand how they invade. And SiO2 is silicon dioxide, and the silicon in the skin, which is 50 times more dense, becomes plated, and it seals the skin. Literally seals it like it's plating a cheap ring, and then the inside begins to get invaded, but only by the tiniest molecules, because that plating is like shingles on a house, and it has a certain permeability, but only the smallest molecules like H2O and OH minus and the very invasive molecules can get in through those little cracks and get in there, and then they do their bonding and destroying of the contents of the organics. It's just the way it works. And other than that, your hydrogen and your volatile organics are sublimated out, and that's what is in the earth as methanes and biogases. All right, so here's what I would recommend you do. If you really want to see about mud fossils and what geology really is, geology has not been presented correctly, and it's going to have to be relearned literally. So you might as well start now. And what you have here is mud fossils, and those are the rocks you're going to find literally everywhere. Now, we went over where they are and where you should look for them. The totally main thing is to find the veins and the arteries. And the veins and the arteries, I went over that, and you can look it up on the internet. One of them is blue and one of them is red. And that's what you're going to find when they petrify in certain conditions. Now, there will be conditions where they'll wash themselves out completely, or they will be from a fire or combusted or whatnot. But there will be these kind of things inside of them that if you open them up, you'll find veins and arteries and all of the evidence that shows that they were alive once. And this is actually literally a tendon enthesis point. And that round ball right there is the enthesis, and that is the stalk. And it comes back up this strappy little fibrous strap. And this was combusted, and this was from a giant phalanges of some sort. And the strap ran in the back, and all the flesh is gone. Have other ones that everything is there. So it needs to be taken a look at, and you can go in your backyard and do this. I guarantee you, absolutely no question, in 15 minutes you will have specimens of your own to start examining, and you can send me shots of them. We'll start a group or whatever you want to do, and we'll share the information about this, because they all petrify in different ways, and all of the tissues in the body are different tissues. Your lungs are made out of primarily blood and scaffolding. And then metals, and there's metals in the blood. It's the way it works. Your bones and your connective tissues are made out of collagen type number 1. It's called, and it's calcium and phosphates and all of the different minerals that give you structural support in your body. Those don't vaporize off like the hydrogen and the oxygen and nitrogen and that sort of stuff, which is gaseous stuff, and that what they call sublimates. It blows right out of your body in vapors. And the arterial blood the arteries are wide open. You cut an artery and it's just going to keep pumping and pumping and pumping, and there's no stopping it. Now, in a vein in your body, it won't stop because it's flowing with the in other words, the veins can't go backwards, and so they clamp off. And you'll find that almost always they'll be black inside these mud fossils. It's just the way it is. So go out and find your own, and then we'll get this thing proven, and then we'll start to understand what our true history is. Because there's a lot more to this than meets the eye. It's not just find some curiosity little thing in the woods, a little bone or something. This is our history. This is human DNA that's been three tests, and I'll show you that right now. All right, there was 3 samples taken. They were very well prepped. They were taken with sterile tools under plastic, deeply drilled, and the density of the DNA was dense, is what they said, for ancient DNA. So the preparation and extraction was textbook. The work that they did here at Helix Biolabs was excellent, and they used the latest techniques and for the recovery of the genetic material. And these are the 3 36-inch tip lung and a mud tip. And this tells all about how they extracted it and And now, once he extracted all of the genetic material, it was sent on to, and here it shows the negative controls were negative all the way through all 3 of them. And here's the sequencing results. Well, I really don't fully understand all this, but all I know is it's 100% human DNA. And if somebody wants to look at this, it's here, and it's up on the website, mudfossils.com. And it goes through the whole thing, and it shows all this business about all the different CTGAs and, sequences and all that business. Now, at the end, it comes up with the fact that they're all 100% human mitochondrial DNA. So this is our history, and this is what needs to be looked at, and you are the people that are going to be able to go out and show that this needs to be seen. Now, there's CAT scans here. All right, this is about a CAT scan. Hold on. All right, there's the finger. I go through the CAT scan of all of this here. It's human giant, 100%, matched, 3 tests discovered in Connecticut, USA. And there's no question what it is. But anyway, I'm not going to bore you anymore with this. But that's, I mean, it shows a fingernail bed. You can't really get any better than that. And these guys, what fabulous, fabulous, fabulous work they did. I can't say enough for them. Jesse Garant and Associates, top of the line equipment, 3D, color scan, everything you can imagine. And they did it in the interest of science, and all I can say is God bless you, my friends, and they were the best people you would ever want to work with. So that's the deal. Go out and find some of these things. Let's go find our real history. Alright, this is the spectral analysis of sandstone, mudstone, and limestone, and these are the 3 components basically of mud fossils. Sandstone, as you can see, has extremely high silicon, Si. And the silicon is from the skin, as I said before, and it goes to SiO2 and it erodes away and forms sandstone. Now you see it's mostly gone in the mudstone and limestone because that's what's left over. But you notice that they're all the same chemistry. You know, the sandstone is not exactly the same chemistry as the others because it has eroded off and is primarily the silicon. Now, I'm not guessing at this stuff. I did this stuff my whole life, looking into crystals and things. Here, hold on a second. What I did was I was in the electronics business, and this is not something that I did. I did it deeply long ago, calculating out all this stuff. I mean, it goes on and on and on. I have lots and lots and lots of information about all of the different things about chemistry and bonding and all of that. So it's not something I don't understand. And I also have done the other work that talks about how things heat and give off heat and absorb heat, and so it's not something I'm not familiar with. So anyway, I'm not showing you that to brag, but it's just everybody says, well, how can this guy say anything? Well, that's how I can say stuff. So go out and find some of this. Let's get it presented. You'd be amazed. Well, hold on one second. A guy found a human head. Hold on a second. Now, that is 100% genuine human head. The guy, his nose is pushed over to the side. He got slammed with something in his forehead, fractured his forehead, and he has a knife blade poking down through the center. We had this CAT scan, and it appears that he has some form of a hat on. Anyway, you could find literally anything, and underneath his neck you'll find all of the different blood situations where blood ran up on the sides of his neck and the vertebra and everything in there, and this is the way blood petrifies. It turns into ferrous oxides, FeO2s and FeO3s, and that right there is bone black, which is the heavily deoxygenated FeO2 blood.